Hello, students. Hope you are doing good. As I promised, I will be sending you a recording on questions which are similar to quiz 4. So far you have been looking at the derivatives, like the first derivative, and then applications of first derivative. Like if the first derivative is positive, you have if your first derivative is positive, your function is increasing, right? If your first derivative is negative, like the slope is negative, your function is decreasing. So you have seen increasing, decreasing functions, and then you have classified your maximum, minimum also using the first derivative test, which is maximum, minimum using the first derivative test is like if of course f prime is 0 at any of these, any of the maximum or minimum. But if f prime increases before and f prime decreases after, so it's increasing to decreasing, you have a maximum. And if it's similarly, if it's decreasing to increasing, you have a minimum in between, right? So let's take an example. The next example would be something like finding higher derivatives also. For example, we will be looking at like the second, we will be looking at the second derivative, the third derivative, and so on. Like from the first derivative, we infer that if it's positive, it's increasing. I mean, we infer many things. We look at the critical numbers, we look at which is maximum, which is minimum, or neither. A critical number could neither be a max nor a min. For example, if we look at f of x equals x cube, right? The first derivative for this is 3x squared, right? The second derivative for this is 6x, and the third derivative for this function is 6, and subsequents are all 0, right? Now if I set my first derivative equal to 0, I get x equals 0 as a critical number, right? Also my first derivative is always positive because it's x squared. So if my first derivative is always positive, it means my function is always increasing. It's never changing from increasing to decreasing or decreasing to increasing. So basically, you don't have a max or min in this function. But there is a critical number. So what is happening at that critical number? Let's see. Okay, so of course, this f prime always positive. F prime is always positive. It means f is always increasing, right? F is always increasing. And but there is a critical number in between. Let's see what's going on. Let's look at the second derivative, set it equal to 0. I get x equals 0 again if I divide both sides by 6. This number, when you set the second derivative equals 0, is called the point of inflection. So setting second derivative equals 0, you get points of inflection. Setting first derivative equals 0, you get critical numbers. So 0 is a critical number, 0 is point of inflection also in this case. Okay, so what does point of inflection tells us? The point of inflection tells us about one important thing, and that's the concavity. So what happens is if the second derivative, let me squeeze in here, if the second derivative is negative, we say the function is concave down. Okay, similarly, if my second derivative is, let me go to the next slide. So if my second derivative is negative, the function is concave down, or I would say the function is sad actually. So concave down means it's like this. If my second derivative is positive at certain number, then it's concave up and it's happy. In between, where your second derivative is 0, for example, in the last example of x cube, your second derivative is 0 at 0, it's changing concavity. It's either changing from up to down or down to up. Okay, let's see what's going on. Again, I'm going to draw a number line over here. Okay, and this is my point of inflection, 0. I take two test points over here. I take a negative one and a positive one. My second derivative for x cube is 6x, right? I plug in both of these numbers on number line and I get negative here. So the function is concave down. It's sad here. and it's happy here because if I plug in 1, I get a positive number. So it means my function is concave down. It's concave down on the interval negative infinity to 0. 0 is my point of inflection. And similarly, it's concave up. It's concave up from 0 to infinity, right? And 0 is my point of inflection. So what's happening with x cube? If I draw my x cube has a critical number at 0, has a point of inflection at 0. It's concave down here and up here. It's always increasing. So it goes like here. Since there is a critical number, the function slows down here. It doesn't turn. There's no max or min. It does not turn. It slows down here and then keep on going up. So there is kind of a horizontal tangent here. The slope is 0, but the function does not turn. Critical number means there is a horizontal tangent, there is a critical number. This is also a point of inflection, POI, acronyms, and that's how your function f of x equals x cube look like. This is concave down and that's up in that interval. Okay, I'll do one more example like this. Let's look at higher derivatives. For example, you want to find this higher derivative or the fourth derivative of this. How would you find the fourth derivative of this? This is your f of x. Okay, let's look at the first derivative. The first derivative of this is, you use quotient rule. So x minus 5 whole squared. So the derivative of x minus 1 is 1, keeping x minus 5 as it is, minus x minus 5, x minus 1 as it is, minus x minus 1 as it is, and the derivative of x minus 5 is also 1. Okay, simplify, x's will cancel, you will have minus 5 plus 1, which is minus 4 over x minus 5 whole square, right? So that's your first derivative. Now for the second derivative, you don't have to use quotient rule again. You can use your chain rule and power rule here. So for the second derivative, this can be written as minus 4 x minus 5 to the minus 2. So use power rule for this function. Negative 2 is the power, so minus 4 as it is, minus 2 power x minus 5 minus 2 minus 1, which is minus 3, right? And the derivative of x is 1. That's it. So which is 8 over x minus 5 whole cube. Similarly, you can find the third derivative. You can use the power negative 3. So I have my second derivative now as 8 over x minus 5 cube, right? Which can be written as 8 times x minus 5 to the negative 3. To the negative 3. Okay. So if I want to find the third derivative, I'll use the same power rule. 8 times 8 is constant, negative 3, x minus 5 to the power of negative 3 minus 1, negative 4. And the derivative of x is 1, right? So you get 8 times 3, so you get negative 24, x minus 5 to the power of negative 4, or you have negative 4 divided by x minus 5 to the negative 4, and so on, right? You can find the fourth derivative or even other derivatives. So that's the concept of finding higher derivatives. First and second we are using, first we are using to find or to locate the local max and local min. The second derivative we are using to find the points of inflection and then checking the concavity of the function. Okay, so let me do one more example. Okay, so my example is f of x equals x cube minus x squared minus 8x plus 5. Okay, let's find the first derivative first, which is 3x squared minus 2x minus 8. I want to graph this function, the function s. So the question is graph f by listing its domain, range, not range, domain. I mean, I can tell you the range also, but domain, intercepts, max-min, point of inflection, concavity, symmetry if any. So first of all, excuse me, that's my first derivative. So if I set this equals 0, what do I get? I can split the middle term. For the product, I need -24. For the sum, I need -2. So -6 and 4 qualifies. So I have 3x squared minus 6x plus 4x minus 8, which is 3x, x minus 2, plus 4, x minus 2, right? And which is 3x plus 4 and x, these are the factors, x minus 2. Okay, so x equals -4/3 is a critical number and x equals 2 is a critical number. Let's see which one is max, which one is min. Suppose this is your -4/3 and this right here is 2. You take test points in between. 0 is definitely in between these. Here you have a 3 and here you have, let's say, a -2, right? So plug in these values. This is the first derivative test. So plug in these red values, the red cross, where I have the red cross, the test points, into your first derivative. So if I plug in 0, if I plug in 0 here, this is gone, I get a negative number. If I plug in 3, I get a positive number. The derivative is, you can make a table also and see what's going on. Your first factor is 3x plus 4. Your second factor is x minus 2, right? If you plug in 0, this is positive, this is negative, so it means the product is negative. When you plug in 3, both are positive, right? So your product is positive, and similarly you'll get positive here. It means your function is increasing here, then decreasing, and then increasing again, right? So your function is, if you want to write the intervals, your function is increasing from -infinity to -4/3 and again increasing, so union 2 to infinity. You can put brackets here. And your function is decreasing in between, which is -4/3 to 2. You can put brackets or parentheses, it does not matter. So in between, it was decreasing. Anad, stop. Beta, holi kar de. Okay, so that's your increasing, decreasing, and your local max is at, so your local max is at x equals -4/3, right? If you go back and look here, so since it's changing from increasing to decreasing at 4/3, -4/3, that's where you have your local max. And it is changing from decreasing to increasing at 2, so you have your local minimum at 2, at x equals 2. Okay, you can find the corresponding y values by plugging in these points into your original function. So, I mean, you can plug in back into your original function, which is right here. You can plug in 2. For example, if I plug in 2 here into this one, I get 8 minus 4, which is 4, 4 minus 16, or 4 plus 5 minus 16, so it's -7. So at 2, you can use your calculators also, so it's 2 -7, xy, this is your x, this is your y, and similarly you can find the xy point for -4/3. So first derivative done. Now let's look at the second derivative of this guy right here, which is 6x minus 2, right? So the second derivative of the same curve that I'm looking is 6x minus 2. Set it equal to 0, I get my point of inflection, which is 1/3, right? So so at 1/3, just plug in your so again do a number line, take test points. Let's take 2 crosses here, this and this. This is 0, and let's say this is 1. Go back, plug it into your original, not original, the double derivative. If I plug in 0, I get negative, so the function is sad here, and the function is happy here. And 1/3, it's changing your concavity, right? So if I want to draw the function, so my intervals of concavity are concave down from negative infinity to 1/3, and concave up from 1/3 to infinity, right? And if I want to draw the graph, I know the domain for any polynomial function is all reals. So domain is negative infinity to infinity, because it's not breaking. There is it's always continuous. A polynomial function, x cubed, x squared, these kind of functions are always continuous. So domain is negative infinity to infinity. Intercepts, my function was x cubed minus x squared plus 8x plus 5. So I can say my y-intercept definitely is your 0, 5. So the function is crossing this point. 2, -7 was your 2, -7 was your local min or max. So 2 was your local min. So x equals 2 and something right here is your local min. At 1/3, somewhere around here, this is my 1/3. Oh no, 1/3 concavity changes. So if I want to draw this, it's something like, and there will be intercepts as well. So this is your local min. At -4/3 is your local max, and -4/3 is right around here. Let's say this is -4/3, this is 2. So and the concavity changes here, somewhere around here concavity changes. It doesn't pass through, so it passes through 5, right? So somewhere around here, something like this is going on, and something like this. So that's the concavity changes right here. So that's where, this is my point of inflection. It's changing from down to up. So it's sad here and happy here, right? And that's my local min. And over here, somewhere over here is my local max. This is the 0.5 y-intercept. Now for x-intercepts, if you can find them easily, it's okay. From your graphing calculators, you can find the zeros. For other calculators, if you cannot factor, that's okay if you cannot factor it. Okay, so don't worry if you cannot factor it. So don't worry if you cannot factor it. You can just roughly draw the graph, or you can, if you're doing your homeworks or if you're doing your projects, you can use your graphing calculators to find the zeros. On the test, if it's easily visible, if these are exact numbers, I will be giving you those kind of questions, or just use your basic calculators to find the y-intercept. But for x, you don't need to find them unless it's very visible. But the process is that you have to use your graphing calculators to find the zeros. For example, this is one of the x-intercept, this, and right here also, that's one of the intercept. Okay, so so that's the graph of your function that I took, x cubed minus x squared minus 8x plus 5, and it has one local min. This is your local max at -4/3, right? This is my -4/3 is your max. It has a point of inflection at 1/3. Okay, so the next question that I want to do is maybe one more of the similar type, or what about this one? Let's see. Y equals minus 3x cubed plus 3x squared minus x minus 2. Okay, one more thing. I think they talk about absolute max and absolute min also. That's just an extension of your local max and local min. Now, for example, this graph, since it goes up indefinitely on both the sides, there is no absolute max or absolute min. Absolute max is the max of all the maximums, and absolute min is the minimum value of all the minimums. So since this graph goes indefinitely on both the sides, there's no absolute max or min. Now, if I restrict this graph, if I restrict it here, so let me use another color. So let's see, if I use this orange, so what I'm going to do is I'm going to restrict this right here. Just take this part right here. Now, if I restrict it here, this point up till this point right here, whatever those intercepts are, let's say this is my A, this is my B, then in a closed interval A to B, there is always an absolute max and always an absolute minimum. For example, in this interval, this point right here, this guy right here, this is a local max, but that becomes your absolute max also, right? And similarly, if I restrict it right here, if I this guy right here, that becomes your absolute min as well, right? It depends what my interval is. Let's take another interval. So now suppose I take, let's use the purple one. Suppose I restrict it from here again and go back this and use this graph right here. You see this one? Now, which is the absolute max? The absolute max now is actually the end point right here. Oops. The absolute max changes to the end point right here, but the absolute min is still the same, which is the minimum, which is at 2. So the point is that absolute min or max, first of all, they always exist in a closed interval. Always exist in a closed interval AB, always. Okay. And not only that, firstly, they are either the local max min or the endpoints. So they occur at either the local max min, depending on how the interval is, or at endpoints. Okay. So let's take another example, the example that I was taking right here. So y equals, my example is y equals 3x cube, let's say negative, plus 3x squared minus x minus 2. Let's find the first derivative, y prime, which is minus 9x squared plus 6x minus 1. And if you factor it, you will get 3x 3x minus 1, 3x, I think you will get something like this. So this guy right here, this line right here is a perfect square of 3x minus 1, and if you factor out a negative, it's a perfect square of 3x minus 1. If I factor out a negative here, I get 9x squared minus 6x plus 1, and that's nothing but 3x minus 1 whole squared. Okay, with a negative outside. So what is this suggesting us? If the first derivative is negative of always a positive number, it means my function is always, first derivative is always negative, so my f is always decreasing. Okay, the function is always decreasing. Critical number is 1/3. So critical number, if I set it equal to 0, 3x minus 1 equals 0. So x is 1/3 is my critical number. And this is my first derivative. That was my first derivative. Second derivative is, again use power rule, minus 2, 3x minus 1. That's my second derivative. Set it equal to 0. I again get x equals 1/3 as my point of inflection. So same point, like it's like x cube example. I have the same point of inflection and critical number. And so if I plug in 0, so if I draw a number line, this is my 1/3, right? If I draw a number line, that's 0, that's 1. If I plug in 0, I get a positive. If I plug in 1, I actually get a negative. So the function is happy here and sad here. It's always decreasing 1/3 is a point of inflection. It's always decreasing, and -2. So it's happy here. It passes through here. 1/3. This is my 1/3 point of inflection. Gets horizontal here, slows down here, and then keep on going down. So that's my function. 3x cube, sorry, -3x cube plus 3x squared minus x minus 2. So that is my function y. It's happy from the interval -infinity to 1/3, because that's my point of inflection, and sad from 1/3 to infinity, right? 1/3 is a critical number. 1/3 is also a point of inflection. Okay. So now if I talk about the absolute max-min, there is no absolute max-min in this. If I restrict the interval, let's say I restrict the interval from here up till here, then whatever the endpoint, this endpoint becomes the absolute max. This endpoint becomes your absolute min. If I restrict. So depends on what your interval is. The highest value is your absolute min, and the lowest value is your lowest is absolute min, highest is absolute max. Okay, so let's do an application problem. Suppose there is a farmer who is interested in, there is a river right here. He wants to enclose a field. One side is along the river. He wants to enclose a rectangular field. He wants to enclose a rectangular field right here, and he has the fencing, and the fence is 1800 meters long. Suppose he has the fencing available as 1800 meters, and he wants to enclose in such a way the area is maximum. Okay, he wants to enclose a rectangular field using 1800 meters of fencing, but area is maximum. Okay, so I want to maximize the area, right? That's what you want to do, maximize the area. Okay, then what's given is, let's say this is my x, this is my x, and this is my y, right? So what's given is the 2x plus y. He wants to use this restriction that the total available fence is 1800 and his sides are 2x plus y. So it means y is 1800 minus 2x. Area of a rectangle is x times y, right? Length times width. So y is 1800 minus 2x, right? So distribute your x. Area is 1800x minus 2x squared. Maximize, find the first derivative, which is 1800 minus 4x. Set it equal to 0. You get x equals 1800 divided by 4. And how much is that? 450? 416, yeah, 450 meters, right? So x is 450 meters. So this side is 450 meters. This side is 450. Total is 1800. That has to be 1800. Also, what is the double prime of your of the first derivative? What's the second derivative of the area, which is this guy right here? It's 0 minus, the constant is 0 minus 4. So it's -4, it's negative. It means the second derivative is negative. It means it's always concave down. The function is always concave down. So whatever we are looking at, 450, it should be it's a critical number. The function is concave down. It means that has to be your local or absolute max right there, right? So x equals 450, and y equals 900 gives you the maximum area, right? So there are some other problems based on optimization. Let me know if you want me to do some. This recording is already 30 minutes. I'm going to upload this one, and maybe we can do WebEx one day, or maybe upload more problems on optimization. Okay, so keep working hard and stay tuned. Let me know if you have any question. Email me, please. Also, please stay active in the class. Complete your homeworks and quizzes on time. And in case you have a question, email me. Okay, take care. Bye.